Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll explain a method to draw a bending moment diagram directly from the shear force diagram. In this method, we draw the bending moment diagram by calculating the area of the shear force diagram. The method is suitable only when the beam is subjected to point loads and uniformly distributed load. When a couple acts on the beam, this method fails since the location of the couple will not be evident in the shear force diagram, and hence drawing bending moment diagram directly from shear force diagram fails. One can assume the couple at any location, and this leads to multiple solutions. So there is no definite solution when a couple acts on a beam. So this is area method for bending moment diagram. So this is best suitable when point loads and UDL acts on the beam. We already know the relationship between shear force and bending moment. Rate of change of bending moment with respect to distance is equal to shear force, that is dm by dx is equal to v. Hence we can write dm is equal to v dx. Integrating integral 1 to 2 dm is equal to integral 1 to 2 v dx. That is integrating from section 1 to section 2. Now integral dm is between the limits 1 and 2. You can write it as m2 minus m1, where m2 is the bending moment at section 2 and m1 is the bending moment at section 1. So m2 minus m1 is equal to this integral v dx. It's area under the shear force diagram between the section 1 and 2. So this integral v dx is the area under the shear force diagram between 1 and 2. So we can write it as m2 is equal to, that is bending moment at section 2 is equal to bending moment at section 1 plus area under the shear force diagram between 1 and 2. So this way you will be able to find out the bending moment at any location. So if you know the bending moment at the previous location or at any particular location plus the area of the shear force diagram between the two sections will give the bending moment at that point. So to calculate the bending moment at section 2, we can use this formula. So bending moment at section 2 is equal to bending moment at section 1 plus area of the shear force diagram between section 1 and 2. Let me explain this with an example. Draw the shear force diagram for the beam shown below and later plot bending moment diagram from the shear force diagram using area method. So this is a simply supported beam with 3 point loads acting on it. Now let us calculate the reactions at the supports. Taking the moment summation with respect to point A, you get 30 into 1. 30 is producing clockwise moment, it's acting at a distance 1 meter away, so 30 into 1 plus 15 into the distance is 4 from the moment center, so 15 into 4 plus 26 into 9, that is the total distance 9, minus Re into, this is producing anti-clockwise moment, so minus Re into the total distance is 12, so minus Re into 12 is equal to 0. So from this you can solve RES 27 kilonewton. So reaction at the end is 27 kilonewton. Now you can sum up the forces in the vertical direction. Plus Ra minus 30 minus 15 minus 26 plus Re is equal to 0. So that is a vertical summation of forces and you can equate that to 0. Now from this you can find out Ra as 44 kilonewton. So Ra is 44 kilonewton. So you got the reactions Ra as 44 kilonewton and Re as 27 kilonewton. Now let us calculate the shear force at various sections. Ra is 44. So if you take a section between A and B, the shear force is plus 44 because this force The force acting left side we are seeing. So this force is 44 kilonewton. So shear force at section AB is 44 kilonewton. Now if you take section BC, anywhere between B and C, 44 minus 30, that is the shear force for that section. This reaction is 44 upward minus 30, that will be the shear force for this section BC. Similarly for the section CD, 44 minus 30 minus 15, that will give the shear force as minus 1 kilonewton. And for the last section DE, 44 minus 30 minus 15 minus 26, that will give the shear force as minus 27 kilonewton. So you have the shear force for the section AB 44 kilonewton, and for the section BC 14 kilonewton, and for the section CD minus 1 kilonewton, and for the section D minus 27 kilonewton. All these shear forces are constant. Between A and B it is constant, B and C is also constant. So everywhere on the beam the shear force is constant for each section, and we got that values, and now you can plot the shear force diagram. So for first section it is 44, so 44, so proportionally I have taken the distance 44, and for the section BC it is 14, so it is dropping here suddenly because of this point load 30 kilonewton. And for the next section CD it is minus 1 kilonewton, so it is below the x-axis, minus 1 kilonewton, and again it is dropping here because of this point load, downward point load. Shear force is decreasing by 15, and here again in this section DE the shear force is minus 27 kilonewton, and from minus 1 it's dropping to minus 27 because of this point load. So 26 kilonewton is a point load acting, it's downward, so it's dropping to minus 27. So this gives the shear force diagram. Now we can plot the bending moment diagram directly from this shear force diagram. So only if the shear force diagram is given, you can plot the bending moment diagram, provided there is no coupled acting. UVL also we can plot, but due to the difficulty in calculating the area, it's difficult when UVL acts on the beam, because you will have parabolic variation for shear force when UVL acts on the beam. But UDL we can do. So point load and UDL acts, you can easily calculate the area of the shear force diagram and calculate the bending moment at various points. So let us do that. So to calculate the bending moment at B, you can calculate the area of the shear force diagram between A and B. So at A bending moment is 0. So to calculate bending moment at B, bending moment at A, the previous location, plus area. Okay. Left hand you can always assume 0, assuming there is no couple acting on the beam. Calculate the bending moment at B as the area of the shear force diagram up to that point, from left hand up to that point. Okay. So bending moment at B is area of the shear force diagram from left hand to that point. So 44 into 1, that is the area of this part, from left hand to section B. The area of the shear force diagram is 44 into 1. So area of the shear force diagram from A to B, that is 44 into 1. It's a rectangle, 44 into 1. So 44 kilonewton meter, that is the bending moment at B. So bending moment at B is area of this rectangle, 44 kilonewton meter. Now bending moment at C is this area from A to C. Total area from left hand to up to that point C. What is the area? This total area. So there are two rectangles. So one is 44 into 1, another one is 14 into 3. The distance is 3. So 44 into 1 plus 14 into 3. Or you can only add this area from bending moment at B is known. Bending moment at B plus area of this rectangle, that is 44 plus area of the next this portion is additional portion. From when you move from B to C, additional area which you have to add is 14 into 3. So bending moment at the previous location, that is 44 kilonewton meter, plus area between B and C, that can be added and you can get the bending moment at C. Or from left hand you can add the total area. Bending moment at A is 0, extreme left hand bending moment is 0. So you just add area up to point C, area of the shear force diagram up to point C from left hand, that will give the bending moment at C. Okay, so you get 86 kilonewton meter. Similarly, you can find out the bending moment at D as area of this shear force diagram up to D from left hand to point D. So this is already calculated. These two areas you already calculated. That is 86 kilonewton meter. That is this summation. So bending moment at D is previous location plus this area. Okay, this area is negative area. So minus 1 into 5. So minus 1 into 5. So this is already previous area. That is these two areas. These two areas, or you can substitute as 86 kilonewton meter. Additional area coming when you move to D is this minus 1 into 5 or 5 kilonewton meter. So totally, if you sum up, you will get 81 kilonewton meter. That is bending moment at D. And bending moment at D is going to be 0 if no couple is acting. Directly you can get 0. Or if you calculate the total area from left hand to this, you should get 0. You can do this from right hand also. At D, the bending moment is this area. If you calculate area from right hand, the negative areas will give the positive bending moment. At bending moment at D is this area, 27 into 3, that is 81, but negative area will give a positive bending moment. That way you should calculate when you consider from right side. So it is easy for you to take from left side. Positive areas will give positive bending moment, and negative areas will give negative bending moment. So add the areas. Positive areas you take positive only, negative areas you can take negative, and then add the areas which will give the bending moment. So to calculate the bending moment at any section, you calculate the area of the shear force diagram from left hand to that section, up to that section. Let us work out another example. Draw the shear force diagram for the beam shown below and plot bending moment diagram from the shear force diagram using area method. So in this case, the UDL is also acting on the beam, 2 point loads and 1 UDL. Now let us calculate the reactions at the supports. So we will take moment summation with respect to A. So taking the moment summation with respect to A, this 10 is producing clockwise moment, 10 into 2, the distance is 2. So moment produced by this 10 kilonewton is 10 into 2, and the density of this UDL is 6 kilonewton per meter, and it is acting for 3 meter. So 6 into 3 is the total load, and it will act at the center of 3 meter. So that is 1.5 meter from here. So from the moment center it is 2 plus 1.5. So that is the location where the resultant load acts. So 6 into 3 is the load, okay, into 3.5. So 2 plus 1.5. So that is the distance from the moment center. So the resultant load into distance from the moment center, that will give the moment produced by this. And then this point load 21 into 5 meter, that will give the moment of that force, minus RD into the total distance is 8, that is equal to 0. So that will give the moment summation. Now from that you get RDS, the reaction at DS, 23.5 kilonewton. So once you get RD, you can sum up the forces in the vertical direction, sigma Fy. That will give RA minus 10 minus this 18, the resultant of this is 18, 6 into 3, 18 minus 21 plus RD is already known, 23.5, so substituting 23.5 and equating to 0, you will get RA as 25.5. So reaction at A is 25.5 kilonewton. So this reaction is known 25.5 kilonewton, and other end it is 23.5. Now you can find out shear force at various sections. Shear force for the section AB is going to be constant, and that will be equal to this reaction. Okay, 25.5. That will be the shear force between section A and B. So for the section AB it is constant and it is 25.5. Section BC, since UDL is acting immediately right of B and immediately left of C, you can calculate the shear force, and there will be linear variation for shear force. And for the section CD it's constant. So let us calculate the shear force. For the section AB, anywhere between A and B, the shear force is going to be the reaction RA, which is 25.5 kilonewton. So this RA is 25.5 kilonewton. That is the shear force for the section AB. Now immediately right of B, without considering this UDL part, immediately right of B, including this point load. So 25.5 minus 10, that is the shear force immediately right of B. 25.5 minus 10, which gives 15.5 kilonewton. So immediately left of C is 25.5 minus 10 minus this UDL part. So immediately left of C, this UDL part you should consider full UDL, you can consider. So 6 into 3, 18, which is acting down, so minus 18. So shear force left of C is 25.5 minus 10 minus 18, that will give minus 2.5 kilonewton. So immediately left of C it is minus 2.5 kilonewton. So right of B is 15.5, left of C is minus 2.5. So 15.5 to minus 2.5 shear force is linearly varying at this particular section BC. Now for the section CD, it's going to be constant. Anywhere you take a section, sum of the forces. So 25.5 minus 10 minus 18 minus 21, and that will give minus 23.5. So when you move from this section to next section, this additional load is minus 21 because of downward force. Minus 21 you can add. From this this minus 21 will give the shear force for the next section CD. So we got the shear force for all the sections. Now let us plot the shear force diagram. So for the section AB it is constant 25.5, but for the section BC you have to consider only right of B and left of C. Right of B it is 15.5, left of C it is minus 2.5. So 15.5 to minus 2.5 is the variation for the section BC. Here we have 25.5, right of B you have 15.5. So there is a drop here because of this point load. So you can draw a vertical line here. So left of C we have minus 2.5, and now for the section CD we know that it is constant and it's minus 23.5. So you can draw a horizontal line here, and this drop is because of this point load, downward point load. So the shear force is changing from minus 2.5 to minus 23.5. So this gives a shear force diagram, and shear force is linearly varying, and there is a point where shear force is coming to 0, and this point you will have a peak bending moment. So between point B and C, bending moment will have a peak, and the variation of bending moment is going to be parabolic. So let us calculate the bending moment at various points. Now bending moment at A is 0. Bending moment at B is area of the shear force diagram up to that point B, from left side, from left end, area of the shear force diagram up to that point. It's a rectangle. Area is 25.5 into 2 meter. So area of the shear force diagram from A to B is 25.5 into 2, or 51 kilonewton meter. So you get the bending moment at this point B as 51 kilonewton meter, and the variation of bending moment is going to be linear because shear force is constant for that section. So you can show the linear variation up to that point. Next, for section BC, it's going to be parabolic, and the bending moment variation is going to be parabolic since the shear force is varying linearly. So you can find out the bending moment at E also, because E we are expecting a peak for the bending moment curve. So to calculate the bending moment at E, you calculate the area up to that point. From left hand up to that point you calculate the area. So you have a rectangle and a triangle. So rectangle area we already calculated 51 kilonewton meter, or 25.5 into 2. That plus this triangle area you should add. But to calculate this triangle area, E is not a marked point. So we know the distance between B and C as 3 meter. So this distance is given, BC is 3 meter. Okay. Now this point E you should locate, or this distance you should calculate. So if you take that distance as D, the B to E, this point where shear force is coming to 0, I marked it as E. So this point up to this point, this distance I marked it as D. We have taken this distance as D from B to the point where shear force is coming to 0. So we need to find out this distance D. Total distance is 3 for the section BC. Section BC, the distance is 3 meter. So the remaining distance you can write it as 3 minus D. The total is 3. This is taken as D. So this is 3 minus D. Now we have two similar triangles. So these two are similar triangles. Now we have 15.5 here and here 2.5. Don't consider the negative sign. These two angles are same. Okay, opposite angle. Tan of this angle is 15.5 divided by D. 15.5 by D. Tan of this angle. This angle is also same. This angle is also same since it is the opposite angle. Tan of this angle is 2.5 divided by 3 minus D. Since angle are same, tan of this angle is going to be same. It is nothing but the ratio of similar sides. Ratio of similar sides means 15.5 divided by 2.5 is equal to D divided by 3 minus D. So that way you can take 15.5 divided by 2.5 is equal to D divided by 3 minus D. Same thing only I have taken, but in a different way. 15.5 divided by B is equal to 2.5 divided by EC, that is 3 minus D. So from this you get D as 2.583. You can solve this and get the D as 2.583. So the distance from B to E is 2.583. So the remaining distance is going to be 0.417 meter. This 3 minus D, or 0.417. Now to calculate the bending moment at E, you have to calculate this area, rectangle area and triangle area. Rectangle area is already known. This triangle area, 15.5 into 2.583, this distance, divided by 2. Area of the triangle is half of base into height. So half of 2.583 into 15.5. So you can calculate the area of the shear force diagram from A to E. 25.5 into 2, this area. Okay. Plus triangle area is 15.5 into 2.583 divided by 2. So that will give 71.02 kilonewton meter. So that will be the peak bending moment. Next, to calculate the bending moment at C, you have to calculate the area up to that point. From left hand, area up to this point. So this area is already known. This total area, this up to E, the area is known. That is 71.02. That is this summation, 71.02. Instead of this calculation, you can take 71.02. So bending moment at C is summation of these three areas. So these two areas is 25.5 into 2, rectangle area, and this triangle area, that's already written here, the same thing I have written. And now this triangle area is, this is 2.5 and this is 0.417. So 2.5 into 0.417 divided by 2, but it is negative area. So minus 2.5 into 0.417 divided by 2. That is the additional area coming, negative area. So this value, so that is summation of this is equal to 71.02 minus this additional area, which will give the bending moment at C, which will work out to 70.5 kilonewton meter. Next bending moment at D is going to be 0. So this is a bending moment at C. If you add this negative area, that is minus 23.5 into 3, and that will be minus 70.5. So already up to area, C area is known, so that is 70.5, and if you add this negative area, you will get 0. No need of calculating bending moment at D, you can assume directly into 0. It will not come to 0 only when a couple acts on the beam. So when a couple acts on the beam, this method fails and you will not get a definite bending moment diagram when couple acts on the beam. So you can draw the bending moment diagram. So here we have calculated it as 51 kilonewton meter, and at C we have 70.5, and at E the peak point is 71.02. So you can draw a parabolic variation with the peak coming 71.02 coming here at a distance of 2.583 meter from B, or from left hand 4.583 meter. From here 4.583 meter from left hand, there is a peak point of bending moment. From 70.5 you can show linear variation because shear force is constant. You can show linear variation and show extend to 0. So that completes the bending moment diagram. And that's all for today. Thank you for watching.